This set of notes is about titrations. You'll find a set of these notes in Schoology for you to use, or you can always take your own. You know the drill. All right, so when we talk about titration, we are talking about a method that is officially known as volumetric analysis, which is kind of exactly as it says, right? We analyze quantitatively things like concentrations, etc., using volumes of solution. So this graphic is sort of showing you that if you know the molarity of a substance, of a solution containing substance B, or a volume of a substance containing substance B, and you know, can then, using titration, figure out the molarity or the volume of it, you can use those to figure out how many moles of substance B you have. If you know how many moles of substance B you have, you then know how many moles of substance A in the reaction that you could possibly be used using the mole ratio. And you could also, from there, use molar mass to get to grams. Okay, but basically, this is a way to use molarities in stoichiometric calculations. Okay, is using molarities and volumes to get you to moles, because of course, molarity equals moles per liter, and so as a result of that, moles equals molarity times liters. All right, so in titration, this is a technique in which you can calculate the concentration of a solute in a solution. Okay, so two different types of titration that we frequently use in chemistry. One is acid-base titration, which basically means that you use neutralization to determine the concentration of an unknown acid or base. So basically, if you know the concentration of an acid, you can add that to some unknown base, and based on how long it takes to neutralize it, you can figure out the concentration of the unknown. Okay, we typically use an indicator. For example, phenolphthalein is an indicator that turns pink when it goes from acid to base, tells you when it's neutralized. Okay, we'll do a lot more of this in our next unit, but this unit we're going to focus on redox titrations. And so basically in a redox titration, use a strong oxidizing agent or a strong reducing agent to eliminate an oxidant or a reductant. So basically you know something that's going to oxidize the molarity of something that's going to oxidize another chemical. You can then use that molarity and the volume of that chemical to figure out the concentration of an unknown. Okay, common oxidizing agents that we use in a redox titration: potassium permanganate, dichromate, and bisulfate. Okay, same kind of thing here, right? We go ahead and put our oxidizing agent into the burette. We start adding it to our chemical, and eventually pink persists, and at that point we know that we have fully oxidized the other chemical. All right, so in terms of how you do mathematics specifically for a titration, you take the volume of the standard solution, that's the one that you know the molarity of, needed to reach the equivalence point, basically the point where the solution turns color. If you then use the molarity of that standard solution with the volume, you can figure out the moles of your standard solute. Then you can go ahead and use coefficients in a balanced equation to figure out the moles of the solute in the unknown solution, and then from there figure out the concentration based on how much unknown solution you added in. To show you how this would work, let's do a quick left side. It says the blood alcohol level can be determined by titrating blood plasma as described up there. The unbalanced redox equation is this. If 31.05 milliliters of potassium dichromate is required to titrate 30 grams of blood plasma, determine the mass percent of the alcohol of the blood. All right, so the very first thing that we're going to have to do here is we're going to have to actually balance that redox equation. Okay, so two pieces that are going to be part of this. We've got the chromium piece and we have the carbon piece, and those are the two pieces of a reaction. If you want to go through and assign oxidation numbers, you can for all of those, but those are the related species that will make up our half reactions. So half reaction 1 is Cr2O7 2 minus goes to Cr3 plus. Okay. And the other half reaction we have is C2H5OH goes to CO2. Okay. All right, so let's go ahead and balance each of those half reactions. First thing we're going to do is balance the chromiums, which is 2. Then the oxygens, which is 7. So we're going to need 7 H2Os. Okay. Then we're going to add in our balance our hydrogens. So we're going to need 14 hydrogens. Okay. And then last but not least, we're going to need to balance out the electrons. And if I do that, I can see that over this side we have a +6 charge. On this side I have a 2 minus and a 14 plus. So that's a 12 plus. So in order to get from 12 plus to 6 plus, we're going to need to add 6 electrons on the left. Okay, so the same thing on the right. Balance our carbons. Okay, then that should say OH up there. Then we're going to do our oxygen. So we got 4 oxygens on the right, only 1 on the left. So we need to add 3 more oxygens with our waters. Okay. And then we go ahead and we do our hydrogens. And so if I count that up, I've got 6 plus another 6 is 12. So that gives me 12H plus. The only thing that we've got charges on here is 12 positives. So that means we're also going to need to add in 12 electrons for negatives. Okay. All right. So basically we've got 12 electrons on the right, 6 on the left. So we've got to double everything on the right. Okay. So that becomes 12 electrons plus 28 hydrogens plus 2 Cr2O7 goes to 4 Cr plus 3 plus 14 H2Os. Okay. Doing some cancellations here. The electrons cancel out. 12 of the hydrogens cancel out. So that's going to leave me with 16 of those. And then I'm going to go ahead and we got some waters too. So 3, and that makes that one 11. So when I get done balancing this, I get 16 H plus 2 Cr2O7, 2 minus, plus C2H5OH goes to 2 CO2 plus 4 Cr3 plus 11 H2O. All right, so now that I've got my balanced equation, now we just have stoichiometry to do. Okay, so they tell me that I have 31.05 milliliters of the potassium dichromate, and they tell me that it's 0.606 molar. Okay, so that's going to give me 0.0600 moles per liter. Problem I have here is that I got milliliters on the top and liters on the bottom. So I got to get rid of that milliliters as well. So we're going to go 1,000 milliliters per 1 liter. That's all going to cancel out, leaving me with mole. At that point, then we have moles of our first substance. Then I'm going to go ahead and I'm going to do my mole ratios. And I'm trying to get, I need the mole ratio of C2H5OH and the dichromate, which is right here. So 2 moles of Cr2O7, 2 minus, 1 mole of C2H5OH. That gets me to moles of that. And then last but not least, they want to know the mass of it. Okay. And so we're going to use molar mass. So 1 mole of C2H5OH and 46.07 grams, which gives me 0.0429 grams of alcohol, C2H5OH, in the blood. Okay, they told me at the beginning of this that I have 30 grams of blood plasma, so mass percent then is 0.0429 grams divided by 30 grams times 100, which gives you a 0.14 BAC, okay, which is pretty high. Well intoxicated at that point. All right, so last thing that we have here is this just a little bit about titrations, notes and some ideas about how to solve some problems with this. That's all you need to know for right now. Please go ahead and do summary and questions on this set of notes. Thanks.